Hi, this is a problem about dynamics of uniform circular motion. When we solve this problem, you'll see that we're basically following the same stepwise procedure that we used in Chapter 4, using Newton's second law to solve a dynamics problem. So pause for a moment and read the question. Okay, so we have a car, and it's going in a turn here. You can see in the picture. And the car is going to go ahead and turn to the left. And you can see that we can look at that curve and consider that to be a section of a circle, right? So here's the curve that we're turning. And if you think about it, right, I guess the circle's actually out here, right, that we're using. That is centered here, right? And so we've got some radius, etc., right? To solve this type of problem, we need to again do an analysis of all the forces that act on the car, which is our object. But whenever we're doing these type of problems, uniform circular motion and analysis of forces, we want to look at the car or whatever the object is from a particular point of view. So imagine that you're watching that car go in a circle, and you want to look at that car either when it's going straight into the page, so you're watching it as it's about to turn left. It could also be coming at you, but in this case we're going to look at this picture right here. So it's a view of the car looking at the tail lights, and it's turning left at the instant here. And in particular, the center of the circle here, in this picture, the center is over in this direction somewhere. Now, again, I'm going to go ahead and do a free body diagram here, or I'm going to draw the forces on for the car. So we've got the gravitational force, Fg, which is, of course, the non-contact force. Now we're looking for contact points on the vehicle. We see that we're ignoring air resistance. The only other thing we see here is the tires in contact with the road. That road is an external object which causes some forces to be exerted on the car. It's a surface contact, and so we're going to end up with two types of forces. One is the normal force, one is the frictional force. And for the normal for both of these types of forces, we know it's actually spread out over 4 tires. We're going to ignore that and just assume we'll draw single force vectors to account for all the 4 tires at one time. Now the normal force we know is going to be pointing in a direction straight up. So here's our normal force. Be pushing straight back up on the car. And finally, the frictional force, well, a little bit confusing about where it might point, but we know that if there's a object in uniform circular motion, there must be a force towards the center which generates this centripetal acceleration. Turns out that actually it's the tires on the road which are pushing towards the center because of friction. And you might wonder, is this a kinetic or a static frictional force? If you want to say kinetic, I understand because the car is moving, but it's actually static because the tires are not slipping. So as long as the tires are not slipping, that means you're not slipping along the surface, and this is actually going to be a static frictional force. And if we read it carefully, what maximum speed can a car safely negotiate a horizontal unbanked turn? Well, that means that we are at the max value of the static frictional force, because if we went any faster, we would start to slip, and of course if you slip, you won't stay in a straight line. You'll start to slide out in this direction, right? Here's what would happen if you slipped. All right, so let's make a nice little free body diagram of these particular forces. So we got gravity, we've got the normal force, and we've got the force of static friction, max. And those are all of our forces there, so there's our free body diagram. Now, one of the things that we do that's particular to this type of problem, uniform circular motion dynamics, we know that the acceleration, it's always towards the center, and the center is over there to the left there, right? And in this case, what we do because of that is we always want to choose one axis that points towards the center of the circle. I typically call this plus r because r is the radial direction, We think of towards the center as along the radius. And so plus r, that means the center is over here somewhere. And then we need another coordinate system that's 90 degrees from that. I'm going to call this one plus y simply because it's up. And that is a good choice for it. But whatever, it just needs to be perpendicular to the r-axis. Now I'm going to go ahead and as usual, figure out a table of these and fill in all the data that we know. So pause for a second. All right, so our free body diagram is the best thing we could imagine. All the vectors are parallel to one or the other axes. And so the first thing that we can always do when we solve a problem like this is write down what the components of the acceleration are. It's always going to be 0 if it's not in the r direction. And we know that we have a formula AC for the magnitude of the centripetal acceleration. It's equal to v squared over r. Sometimes there's a little bit of question about whether we should call this r or c here because it's in the r direction, etc., right? But this goes right here. V squared divided by r. That's the magnitude of the centripetal acceleration, which points towards the center. So that's AC or A sub r. Always going to have these two here for this type of problem. The other ones, they're all aligned with the components, so let's figure them out. For the force of gravity, of course, we have 0 in the r direction, right? And it's all in the y direction. And we know that the magnitude of gravity is mg, right? And it's down, so it's negative mg in the y direction. For the normal force, we don't have a formula for the magnitude, so we're going to just have to leave it as an unknown, Fn. But we do know that all of that magnitude points in the positive y direction, so that means that we've got 0 for the r-axis, and we've got plus Fn over here for the y component. And for the Fs max, we see again that there's a 0 along the y direction. And we actually have a formula for Fs max. Remember that Fs max is equal to, oops, let me write that better. We look this one up, mu sub s times magnitude of the normal force. So all of that magnitude for the static frictional force max, it's going to go in the positive r direction. So we've figured out these things here, and some of this stuff we already know, right? We already know what mu sub s is. We don't know what m is, right? We do know what g is. We don't know what f sub n is. What are we going to do next? Well, we're going to go ahead and plug these into Newton's second law. So let's go ahead and do this. I'm going to start with the y direction because that one looks easier. So if I do the y direction, mass times ay is equal to sum of the forces in the y direction. And immediately we see that the acceleration is 0, so that's great. 0 is equal to, now let's sum up all of the y components of the vectors for the forces. And if we do that, we see, okay, we got a minus mg plus an Fn plus a 0. And this tells us that the normal force in this case is exactly balancing the gravitational force. So the magnitudes are the same, and that makes sense. That's why we drew the two vectors with the same length for the normal and the gravitational force, because we know it's balanced in that direction and they're equal and opposite. Let's do for the x direction here. So separately, Newton's second law, m, actually I should call this the r direction, sum of the forces in the r direction. By the way, this here is what we call the centripetal force. Sometimes we write it F sub c, right? F sub c is equal to all the sum of the forces in the r direction here. And so let's go ahead and continue down here. Now, I don't know what the mass is, right? That's okay. If you don't know what something is, just leave it as a variable and keep on going. So AR, I'm going to go ahead and plug in this, right? Because that's the component along the r direction. And then over here, as usual, we're going to go ahead and add up all the forces. Okay, we add them all up. Well, there's only one, mu s Fn. Okay, looks like we're not quite sure yet. We're trying to figure out here the maximum speed the car can safely negotiate. So we are certainly looking for v, which is there. Good. We know what r is, so check that. We don't know what mass is. What can we do here? Well, you know what? We got two equations. Let's go ahead and do a little substitution. We'll take this. We'll substitute it in over here. And hopefully our mass will cancel out since we don't know what it is. Let's see what happens. So we're going to end up here with a m v squared over r is equal to mu s times, when we plug in from the other equation, mg. Aha, look what happened. The mass just canceled out. So we didn't need to know the mass because it canceled out. And finally, we can solve for the speed here. So to go ahead and do that, we're going to write this as v squared is equal to r mu sub s g. And finally, we need to take the square root of both sides. We take the positive root because this is a speed, and we find out the speed is equal to this, r mu sub s g. And for part A, we can go ahead and plug in our information. So mu sub s for part A. This is when it's dry weather. That means you have a large value of the static coefficient of friction, which means there's a stickiness. There's a good grip between the tires and the road. And so let's plug those numbers in and see what we get. So inserting our known values, putting them in the calculator, we end up with about 22 meters per second, which is something like 45 miles per hour, right? Great. So we just got the dry conditions. What about for the next one? What about when the conditions are icy? That lowers the coefficient of static friction because it's more slippery between the tires and the road, right? Do we need to go ahead and redo this entire problem the way we just did? We don't actually need to, because the only thing that changes is this. This is the only change when we go to the wet conditions. And therefore, all of the other analysis is going to proceed the same. We're going to come up with the same exact result here. And so we don't need to redo everything. All we need to do is take the same result and put in the new condition. So we're still using this equation. Only thing that's changed here is the value of the coefficient of static friction is now 0.1, a lower value. And when we put this into the calculator, we see now the max speed that we can go without slipping is 7.1 meters per second. We're talking about 15 miles per hour. And of course, this is why you got to be careful when you are driving on a slick road. Now your peer review problem for this week is similar to this problem. You're going to follow all the steps, draw the picture, right? Identify the forces, do a free body diagram, figure out your components and put them into a table, and then apply Newton's second law and solve the equations for the unknowns. Let me help you out a little bit just to kind of visualize that problem here. Where should we do it? Maybe right over here. So let's go ahead and this is what your problem looks like. It's an airplane going in a circle. In this case, we've got the visualization of the airplane as it's coming straight towards us. It's about to turn to the left, right, in that circle. And again, I've put the r plus r and the plus y coordinate system in there. You're going to need to figure out the forces. Well, in fact, one of them is already drawn for you, right? This is your lift force, which is generated by the wings, and the air is pushing it in that direction, right? The only other force you got to worry about is your non-contact force, gravity, so draw that in there. And in this case, again, we've drawn the component, radial component here. Remember, you're going to have to do a little bit of trigonometry here to figure out what are the components of L. This is going to be, what, 68 degrees here? You want to use this triangle to get the components of L. Ly, and here is Lr. Well, that's the important one that points towards the center. That's going to be in the column with R. And essentially, this is the same type of problem. Only difference is in this case, the lift force is not already completely aligned with R, so you have to do trigonometry to figure out what is the Lr component, what is the Ly component. This is the first quadrant because these are both plus, right? So we know this would be plus plus. We know that this is going to be L, the magnitude, and finally we got to put in the trig functions next, right? And you guys know how to do that, so I'll let you work on that.